Welcome back, class. Today we're going to talk a little bit about the graphs of antiderivatives. And it's going to turn out that there's not so much to talking about the graphs of antiderivatives because they line up exactly with the stuff about graphs of derivatives. Okay. So before we even get to talking about graphs of antiderivatives, I'm going to start by doing a question just to remind you how it looks when you do a question of the form sketch the graph of the derivative. Sorry, this is meant to be f. Okay, so I have a graph of f. I want to sketch a graph of f prime, and I want to think about how the derivative is connected to the original graph. Okay, and so really here I'm just sort of thinking about doing a 140 problem again. Okay, so I recommend here when you do this that the first thing you do is you identify all the spots where the derivative is 0. So that is spots where the tangent line's horizontal. So there and there, those are my critical points. And so in the graph of the derivative, which I'm going to put in blue, that point is on it because the derivative here is 0. And this point is on the graph because the derivative here is 0. Okay. And I recommend, just like we do with the first derivative test, sort of break your graph into pieces along these points. Okay, and think about what's happening between here. Well, in this middle piece, everywhere the tangent line, if I let the marker be the tangent line for a minute, everywhere the tangent line is negatively sloped, the function, if you like, is decreasing over this period. So the derivative is negative. Okay. So I know that when I draw the graph of the derivative of this piece in the middle, it's going to live entirely in this zone. It's going to live entirely down here somewhere. Okay. Likewise, when I go to look at this piece, here the function's increasing, so the tangent line here has positive slope, which means the graph is going to live entirely up here in this piece. And the same actually goes for over here. This function's increasing, the slope is positive, so the graph of the derivative is going to live in that zone. Okay, so now I just have to think about what the graph actually looks like. So I know I need to connect this point to this point in the middle. Okay, so here the derivative is 0. And then I want to think what happens as I move from left to right. Well, here the derivative is 0. Here it's negative. And of course it's negative, it's negative, it's negative, it's negative, it's negative. But I want to think how big is it? So here it's 0. Here it's negative, but it's a little negative. And it's a little negative because the slope here is shallow. And so it's more negative here and more negative here. And that, in fact, is actually the place where it's most negative. And then it's less negative, less negative, less negative, 0. Okay. And so that story is the derivative starts out being 0, it becomes negative and more negative and more negative until a point in the middle, in fact, the inflection point, if you want. And then after that point, it becomes less and less negative until it's back to 0. So I have described for you basically a parabola shape that looks something like that for the derivative. Now, over on this piece, here the derivative is 0, and then the graph here I see is getting steeper and steeper and steeper and steeper. And so that means that the derivative is positive and becoming more positive. So the derivative is going to go up like that. And the same thing happens over here. The derivative starts out very positive and becomes less and less positive because this becomes less and less steep. So it continues over here, something like that, more or less. Okay. This is probably not too surprising because, again, you've certainly thought about this a lot in 140, and also you've probably pretty much internalized the idea that if you take the derivative of something that looks like a cubic, it shouldn't be too surprising when it works out that the graph is some sort of parabola, because that's a quadratic. Okay. But I want to think about this the other direction. So I'm going to start here with a function. So this is going to be my function. And, well, that's the axis. That's not the function. Here's the function. This is f of x. Okay. And now I want to sketch the antiderivative. Okay. I did not label this. I'm going to go back here just to be super clear. This thing we drew, this is the derivative. Okay. Now I'm going to, instead of doing that, I'm going to go and sketch the antiderivative. Okay. And when you're sketching an antiderivative, remember there's actually lots of antiderivatives. Those antiderivatives differ by a constant. And if you think about what that constant would do to the graph, it actually shifts the graph up and down and up and down. If you want to think about it in terms of this graph, actually, if I shifted the black graph up or shifted the black graph down, neither of those would have any impact on the blue graph, which is the derivative. Okay. As a result, when someone asks you to sketch the graph of the antiderivative of something, they have to tell you a point on it. And almost always the point they tell you is, hey, make the graph pass through the origin. So the first point we're always going to draw on our graphs of the antiderivative is the graph is going to pass through the origin. Okay. So now the function I'm going to try to draw, this line is the derivative. Okay. So if you want even, I could call this f prime and the function little f. I'm going to make it the antiderivative, so I'm going to call it big F when I label what the graph is. Okay. So I have to think about what this piece of the graph here is telling me. I know something special is going to happen at this point where the derivative is 0. Because the derivative being 0 is where all of this exciting stuff happens. But I'm going to pause on thinking about the exciting stuff for a moment, and I'm just going to think about what's happening on this piece. Okay. And so what's happening on this piece is that the derivative is positive all the way across here. So when I go to draw the red graph, it had better be increasing everywhere up until this line. But what I also can see is that this value is getting smaller and smaller and smaller. And what that tells me is this function, it's actually, although it's always increasing, it's increasing at a slower and slower rate. Okay. Until when it gets here, the tangent line is supposed to be flat. So it should look something like this. And so something parabola-y like that, with a horizontal tangent line here at this point. But now at this point, the function switches from, the derivative switches from positive to negative, so the function I'm drawing, the antiderivative, switches from increasing to decreasing. And so it starts off decreasing very slowly, but then decreases faster and faster and faster. And so it ends up looking like that. And so what you're going to end up with here is you're going to end up with some sort of downward pointing parabola, and that will be our antiderivative. And now it should be the case, at the end of the day, that if, say, I give you this function to start with and ask you to draw the antiderivative, you should then be able to hand your answer for the antiderivative to a classmate and say, hey, now sketch the graph of the derivative, and their graph of the derivative should look back like the graph you started with. So exactly the relationship between the red line and the black line is the same as the relationship in the previous graph between the black line and the blue line. Namely, we just at the end of the day are saying, okay, in this graph, the black is the graph of the derivative of the red, in the same way that here the blue is a graph of the derivative of the black. Okay, I'm going to do a couple more examples of this. Uh, okay, so this is my f of x. And I want to try and draw the antiderivative of this that's going to pass through the origin. Okay, so that means it's going to pass through that point right there. Okay, and I've got to think about, again, what the graph of the derivative, because this black graph is the derivative of the function I'm graphing, what does that tell me? Okay. Well, over here, over this piece, and I'll just go ahead and, sorry, this point is not on the graph. I'm going to go ahead and draw my graph in blue just so that we don't get confused. So this point is really on the graph of the antiderivative. That one's not, but here the derivative is 0, so I'm going to go ahead and break the graph up at this piece just like we've done on all the previous ones. Okay. So here, this black graph, the graph of the derivative is positive, and so what that tells me is that the function's got to be increasing on this whole piece. So my function's going up, and so it's increasing to the origin. But if I look at it, it's increasing at, and then here it's increasing at a slower rate, but then over here it's increasing at a faster rate. So what that's going to correspond to is here, the tangent line has to be horizontal. And then back here, it's increasing at the fastest rate, and then it's got to go back to a point where it's increasing at a rate of 0. So where the tangent line has 0 slope there, because the derivative is 0. Okay, and so this sort of S shape here is corresponding again to the fact that there's an inflection point here in the graph, and that inflection point is corresponding to that point up there on the graph of the derivative of my blue function. Okay, and so here again, it was increasing slower and slower and slower from this dot onward, whereas over this piece, it was increasing faster and faster. Okay, but now at this point over here, the derivative is now negative, so my function's now decreasing. And in fact, it decreases faster and faster and faster and faster, so I end up with something that looks like that. And in fact, over here, now the derivative is negative, so it is going to do the same thing, where it is going to decrease faster and faster and faster. And that is a graph of our derivative. Okay. Sorry, that's a graph of our antiderivative. Apologies. Oh, I looked at this backwards. So I will fix this. So I said here the derivative is negative, so the function is decreasing, except then I proceeded to immediately draw a function that was increasing because I was looking at it backwards. So this is not decreasing. This would be decreasing. So I've got something like that. And so this is my antiderivative. Okay. And don't read anything into the arrows. I just put arrows sometimes and not others. Okay, so there we go. Decreasing while the derivative is negative, and then switches to increasing while the derivative is positive, having an inflection point here, and then going back to here. Okay, and let's do one more example here, because I know people like as many examples of things that involve graphs as possible. I'm going to draw my axes here. I'm going to draw my graph. It's going to look something like that. So this is my f of x. Okay, and I'm again going to sketch the antiderivative. So I'm going to start with this thing going through the origin. Okay, and it's increasing because the derivative is positive. So my red function is supposed to be increasing, but it's supposed to be increasing at a decreasing rate because the derivative is getting smaller and smaller and smaller. And so it is going to increase, but at a decreasing rate, decreasing rate, decreasing rate, decreasing rate, until the rate is supposed to hit 0 at exactly this point. Because here the derivative is 0, so the tangent line to my graph is supposed to be horizontal. Okay. And now the thing we do almost on autopilot is to continue this down so it looked like a parabola. But that's not actually what happens, because over here, again, the derivative is positive. And so I start here with a 0 derivative, and then the derivative increases slowly. So I start increasing again, and then that derivative increases faster and faster, so it becomes bigger and bigger. Okay. Over here, I just sort of continue it. There was nothing sort of special about that piece over there. Okay. But this is one of those critical numbers that often ends up being confusing to us because here the derivative is 0, even though it's not a local min or a local max. This is one of those spots where if we were doing the first derivative test, we'd say, oh, this is a critical number where the function switches from increasing to increasing because the derivative was actually positive on both sides. All right, we're going to call that good for this lecture on graphs of antiderivatives and indefinite integrals or whatever you want. Next time, as promised, we're going to pick up with the other kind of integral. So we've been talking now for several lectures about indefinite integrals. We're going to pick up next time and talk about definite integrals. Until then, though, be well.